All right, welcome back to the beginning of Unit 2, our discussion on polynomial equations. So in Unit 1, we took a look at polynomial functions, and mostly what we were looking at there was the relationship between the pictures, the graphs of a function, and the way the function looked, so the numbers in the function. And in this unit, we're going to focus more on the algebra of playing with polynomial equations. So there is a fair bit of overlap between the two. Arguably, these could be taught as one giant unit, but we split it up just to make things a little bit simpler. So we're going to start by taking a look at polynomial formulas. So that basically means any formula that appears in polynomial kind of notation. And how they work is pretty straightforward and relatively quick. So we're just going to jump in and kind of do some examples. But before we do that, I want to make sure that we know a few things. And we're going to start with some basic terminology of exponents, and then a little bit of review of one of the exponent rules that we learned back in the previous grades. So first of all, if I say something like 5 squared right here, a lot of people use a few of these words interchangeably, but to be technical, we should know what the words mean. And I will try to use proper terminology, although my mathematical slang is pretty strong, so we'll see what ends up happening. But when I see 5 squared, the base of that is the 5. The exponent is the 2. And a lot of people will say that the power is 2. It's common slang to say 5 to the power of 2 when we really mean 5 to the exponent of 2. Despite that, most people will still say power of 2, and that's okay. We're not going to freak out because there will be nowhere on a test where you have to say the words. But we should know that the power is actually referring to the entire thing, 5 squared. So 5 to the exponent 2 is a power of 5, meaning that it's 5 to some exponent. So the word power actually refers to the whole thing, not just a piece of it. All right, so going to one of our exponent rules, you may recall this back from grade 9 or 10. If we have two powers, I want to make sure I'm using the terminology right, two powers with the same base, all we have to do when we multiply them together is add the exponents. I'm going to do this in a slightly long way, just to show you that it works. But 2 to the 4 really means 2 times 2 times 2 times 2. And then we're multiplying that by 2 to the 6, which is 2 times 2 times 2 times 2 times 2 times 2. And if you count those up pretty quickly, I think you'll see that there's 10 2's all multiplied together. So that's going to be 2 to the exponent 10. So in general, anytime we've got the same base and we've got exponents on those and we're multiplying those powers together, we add the exponents. So x to the exponent m times x to the exponent n is x to the exponent m plus n. And again, you can always go back to this idea of first principles to see how it works if you forget. That's one of the things I like about math, is that there's a lot of times where you can deduct what's going on just by actually writing things out and doing it from like an older form. Okay, so just to do a couple examples super quickly. X squared times x to the power of 4 is just x to the power of 6. Just add those exponents together. Now here we've got some coefficients. We've got a 2 in front of our x cubed and a 3 in front of our x to the 6th, but multiplication is multiplication. Order does not matter, so we could do this in any order we want. 2 times x cubed times 3 times x to the 6th could easily be done as 2 times 3 times x cubed times n to the 6th. X to the 6th. Tongue twisters today. 2 times 3 is just 6. X cubed times x to the 6th is x to the 9th. Add the 3 and the 6 and you're good to go. Similarly here, I can do the coefficients first. Negative 4 times 6 is negative 24. And now I have to add the exponents. Be careful on this one. A lot of people will say, well, there's an exponent of 2 and an exponent of 3 and no exponent, so 2 plus 3 is 5. But remember that a variable with no exponent is really to the exponent of 1. So we have to add 2 plus 3 plus 1 is x to the exponent of 6. For part D, similar to the coefficient thing, if we have multiple variables, we can treat each of them separately. So we'll just do the power of x first. And we have x squared times x is x cubed. And then we can do the y's. Y to the 6 times y cubed is y to the 9th. Okay, that wasn't too bad. All right, polynomial formulas. So I'm going to point out that we actually have been using polynomial formulas, whether we thought of them as that or called them that, since back to at least grade 9. So the first example we're going to look at, and actually several of the examples we're going to look at are from geometry. Now I will remind you, or I guess I haven't told you before, but we're going to be doing geometry later in the course. It's going to come up a little bit closer to the end. So we're going to go through all the details of that then. For now, I am going to use some of the formulas, but I will give them to you so you don't need to memorize them or know them for anything. In this particular example, we need to know the area of a circle equation. But you have seen them all before. There won't be anything that's new, but we're not focusing on the geometry part. We're just using it as an application for our polynomials. Okay, so the formula for the area of a circle is area equals pi r squared. Let's take a look at a few things about this. Now, there's 3 things in here, and I'm going to say this, and I'm warning you it's improper. There are 3 variables here, a, pi, and r. They're not actually all variables, though. So let's just see what each of those stands for. And a, we can figure out, is the area. And in this particular equation, if we think of this as a function, is actually an output. It's what we're finding when we plug in something else. By the way, you don't need to write that on a test. I'm just pointing out that that's the case. Pi is not actually a variable. It's a constant. And it's 3.14159, etc. And for our purposes, if you have a pi button on your calculator and you'd like to use it, fantastic. If you don't have a pi button or you don't want to use it, feel free to round this off to 3.14. It's a little bit of rounding error, but it'll be close enough that it won't affect any of our answers. Okay, and r is the radius of the circle we're looking for the area of, and it can be thought of as the input. We put in the radius, we square it, we multiply by pi, we get out the area. So what type of polynomial is this? Remember back in the last unit, we looked at the names of different types of polynomial functions. We started off with the basic linear, and then we went up to quadratic, cubic, quartic, and then after that, we just say things like degree 5, degree 6, degree 7. Now in this case, the input variable r has a square on it, and that means that this is a quadratic. So even though we may have never thought of this back when we first started using it, a equals pi r squared is a function, and it's a polynomial function, a quadratic function. Now, remember that when we talk about domain and range of things, we often say things like, what values break the equation. And technically, the equation will give you an answer no matter what value of r you put in. So you could argue that r is the element of all real numbers. However, in real life, we don't do that. What would the realistic input be? And for a circle, again, you can maybe make an argument about this. You could say that r has to be greater than or equal to 0. I'm going to say, just for the heck of it, that we're going to say x, or in this case, we want to use the variable in the equation. R is the element of real, such that r is, I'm going to say, strictly greater than 0. Now you could argue r is greater than or equal to 0. I'm going to say it's got to be strictly greater only because a circle with a radius of 0 isn't a circle. It's nothing. There's nothing there. If I say, on this piece of paper, I have a circle with a radius of 0, all pieces of paper have circles of radius of 0 on them. There's just nothing. So I'm going to argue that it should be greater than 0. You could argue it be greater than or equal to. Either way, none of them will break the equation, but just to be realistic, that's what I'll put in. And immediately I make you fill in a table of values given different r's. You know what? Okay, fine. I guess I'll put in the optional greater than or equal to. Let's dismiss that random pop-up there. Okay, so if we plug this in, remember that we just do area equals pi r squared. So in this case, it's going to be pi times 0 squared equals 0. And then the rest of these, I'm going to kind of do manually just to save a little space. Pi times 1 squared is 1 pi. Pi times 2 squared, which is 4 pi. Pi times 3 squared is 9 pi. And pi times 4 squared is 16 pi. Now it's asking us to make a graph in the next part. So let's just really quickly, I think I can do this one here, 3.14. And double that would be 6.28. And I'll pull out my calculator for the next one. Oh, sorry, that's not double. It should be quadrupled. 3.14. That should be 12.5. I guess it rounds up to 12.57. And 9 times pi is 28.27. By the way, I'm using the actual pi button on my calculator, so if you're using 3.14, it'll be slightly different, but not enough to matter to us. 16 times pi is 50.27-ish. Okay, so for this one, sketch a graph of the function. I think we can do a really quick sketch on this. I'm just going to do a graph that looks like that. Our input, our radius will go as our input or on our horizontal axis, and our area will go on the output, our y-axis. Traditionally, we call them x and y. Here, we'll call them r and a. And my radius has to go from 0 to 4, so I'm just going to go 1, 2, 3, 4. Again, this is a sketch, so we're not going to be super neat about it. You don't need to pull out a ruler or anything. And our y values are, in this case, our a values have to go up to 50.27. I don't know if I'm even going to notice the 0.27, so I'm just going to take my graph up to 50, and I'll go up by tens. And I tried to make them relatively the same distance apart, although I think I may have not succeeded greatly there. But that's what rough sketches are for. So I'll plug in the values here. 0, 0, 1, 3.14 takes us about a third of the way to 10. 2 and just over 10, 12 point something. 3 and 28 takes us up to about there, give or take. And 450 takes us up to about here. And if I connect those with a nice curved line, I'm going to get something that looks like that. And sure enough, that looks like basically half a parabola. Okay, so we have our first quadratic function. Notice that I'm using functions right now. I said we were getting into polynomial equations, but we're still going to keep thinking about things as functions. Question 2. In some professions, you can retire with a full pension when your age plus your years of service total a certain number. For example, a job might have an 85 factor. A formula to represent this could be S plus A equals 85. So your years of service plus your age equals 85. When that's true, you can retire. So you could start working at 84 and retire at basically half a year later at 84 and a half with half a year of service. Very few people do that, because it's hard to live until 84 and a half with no income. But for most people, you would, for instance, start work maybe say around age 20 or 25 if you're doing a degree, and then you'd work for about 30 years. So you'd have 30 years of service and be about 55 years old. And then you'd retire at 55 with a total of 85 between the two. So what type of polynomial is this? Well, this one's a little bit trickier to see because S and A, I don't know which one the input and which one the output is, because the way that it's expressed, S plus A equals 85, doesn't really isolate one of the variables. But no matter which variable it is, I know that it's going to be a linear relationship. So I'm just going to write that down, because I see no squares or cubes or anything else. So now we can choose to rearrange that formula to isolate either variable. In this case, we want to rearrange the formula to find the retirement age as a function of the years of service. So we want the A by itself. And I'm going to try very hard to make my S look like an S and not a 5, which is something I'm actually quite horrible at. Okay, so from there, if I want to get age by itself, age is a function of S. I'm going to just subtract S from both sides. So age equals 85 minus S. And while that equation is perfectly good, if you'd like to write it as a function, A at S equals 85 minus S, you're more than welcome to write it in function notation. So then the question is, how many years of service would you need to get to retire at age 55? And I think I kind of already answered this question with my random example at the beginning, but how many years of service do we need means the S is unknown. The retirement age is 55, so we plug in 55 for the A, or A at S, equals 85 minus S. In this case, I'm going to add S to both sides and subtract 55 from both sides. And so years of service would be 30. Okay, what age can you retire at if you start working at 28? Okay, so let's set up our equation. A is the unknown. Now here's kind of where it gets a little bit weird. We know our equation is 85 minus S. Okay, so we want to figure out what age is. One sec here. And really, this is kind of hard to solve because what's the variable even here? Or what are we going to plug in? So just as a little aside, I'm going to put down that the number of years of service that you're going to do. By the way, mathematicians do this all the time where they kind of do something kind of separate from the problem they're working on. So they plug something back in and we call those an aside. So the years of service is going to be, in this case, for this person, your age minus 28. So if you think about it this way, if you start working at 28, by the time you're 30, 30 minus 28 will give you 2 years of service. By the time you're 38, you'll have 38 minus 28, you'll have 10 years of service. So if we go back over here, A equals 85 minus S, but S is A minus 28. Just rearranging this a little bit, 85 minus A plus 28. Don't forget, we put that negative inside both terms in the bracket. And then what I'm going to do is add A to both sides to get 2A over here, and then minus A on the right goes away. 85 plus 28 is 113, I think. And then I'm running out of room, so I'll make a little arrow and continue my equation over here. 2A divided by 2 equals 113 divided by 2. And the age in this case is going to be 56.5, I believe. So 56 and a half. Incidentally, I created this question not to be completely hypothetical. The job I work in does have an 85 factor, and I did start working at 28, so I can retire with full pension at 56 and a half. Although I think I'd rather retire earlier because I don't need the money, but I do like my sanity. Okay, going on to question 3. Back to something that at least feels a little bit more concrete, another geometry thing. Now, here's an equation you probably don't remember, but that's okay. You don't need to memorize it. I'm giving it to you in the question. And that's the surface area of a cylinder. So just as a quick reminder and a little foreshadow of our geometry unit that's coming up later, this is actually made up of 3 separate parts. If you think about what a cylinder looks like, I'm just going to draw a cylinder over here. Looks like that. And the 2 pi r squared comes from the area of the top circle, which is pi r squared, the area of the bottom circle, which is pi r squared. So there's 2 pi r squareds. And then the 2 pi r h, 2 pi r is the circumference of the circle. So that basically the distance around the outside is 2 pi r. And then the height is h. And if we actually cut this cylinder, like if you think about this like a toilet paper roll, if we cut it down the side and then stretch it out, we get a rectangle, and its width would be 2 pi r and its height would be h. So that's where the 2 pi r h comes from. Okay, a company makes cans that are 4 inches tall, but all have different radii. So we got a whole bunch of cans that are all the same height, but different sizes. Some of them are very big and some of them are very small. So we're going to modify our equation slightly. First, though, we're going to mention that what kind of polynomial equation is this formula if we do this. If I look at the equation, well, if I know that the height is, you know what, actually, let's maybe do part B first. That might make it a little bit easier. If I know the height is 4, then the surface area A is going to be 2 pi r squared plus, if I replace the h with a 4 and then I multiply it by the 2 out in front just to save a line, that'll be 8 pi r. So there's no h anymore because I know that all the cans it makes have radius of 4, height of 4. So I don't need to worry about leaving that variable there. Now if I look at that equation, 2 pi r squared plus 8 pi r, remembering pi is just a constant, this is something r squared plus something r. This is a quadratic formula. All right. If a can has a diameter of 3 inches, how much aluminum would be needed to make it? Okay, just as a quick aside here, we got to be careful that the number we're given in the question isn't actually one of the variables we have. We're told that the diameter is 3 inches, but we need the radius, and I think it's pretty easy to see that it's going to be half of that, 1.5 inches. So that's all we have to do is plug in 1.5. Now again, if you think about the area as a function, we could put area at radius, or in this case, area evaluated at 1.5, but we just plug it in as well. Okay. From there, literally just punch it into your calculator and you get 51.84 when I round off to 2 decimals. I could have rounded that off to 51.8 as well, or even pretty much 52. But the units are going to be inches squared, or square inches. Okay, so the important part about this, actually, from our point of view, isn't necessarily all the little details. It's recognizing that this is actually a quadratic function, that it's going to act like a quadratic, it's going to go up as a square, even with that little bit of extra on the end. Now here we've got a second company in question 4 that also makes cans. They work a little bit differently. All of their cans are 4 inches in diameter, but their heights are different. So they make them in a completely different way. Okay, so again, remember that if the diameter is 4, that's really the same thing as saying that the diameter is 8, radius is 4. And again, I think we're going to skip part A for just a second and go to part B. If a can has a height of 1.25 feet, we keep working in weird units here. 1.25 feet is 12 inches per foot is going to be 15 inches. Okay, so our formula, if I go back up here, we had 2 pi r squared plus 2 pi r h. And this time we're told that all of our radiuses are going to be 4. So that means that before I even start to solve for the question part B, I'm just going to get a formula of 2 pi 4 squared plus 2 pi 4h, which is going to be 16 times 2 is 32 pi. I'll leave pi as a constant for 1 second instead of multiplying it out. And this is going to be 8 pi h. Now, if you want, you don't have to do this right now, but we can at some point do it. 32 times pi is 100.53. And 8 times pi is 25.1. So 25.1 h. So there's our simplified formula. It's not even answering the question about the 1.5 feet tall, but now we can see that the only variable on the right-hand side is h. So really, there's no exponent on that h. This is a linear function. All right, let's answer the question, and then I want to go back and point something out. Okay, so for this particular question, we're now told that the height is 15 inches, so we'll just say A equals 100.53 plus 25.1 times 15. 100.53 plus, throw that into my calculator, that's 376.5. And when we add them together, we get 477.03, which I think I could round off pretty easily into just 477. Either way, final step, the area is 477 inches squared. Okay, so I want to point out that we had two different companies here that made different cans, but they're both cylindrical. One just keeps the radius constant, one keeps the height constant. And in one case, we got a quadratic function. In one case, we got a linear function. So going back to the original equation there, this is where it gets weird. Is that a quadratic function or is it a linear function by the way it's written now? And the answer is without specification, it's neither. And again, it's not something we get into a lot, really, at least as far as the actual math goes. But here, area is really a function of both r and h. So it's a function of two different variables, and we can talk about it being linear as a function of height and quadratic as a function of r. So it depends which one of those is held constant, which one we're allowed to change around. And if we graph both of those, an area with a constant height, we get a nice quadratic parabola. And if we do area with a constant r, we get a very straight line for different values of h. So again, to look at a single equation and say, is it a function or is it a linear or a quadratic function or something else? If it's got multiple variables, it depends what variable you're talking about. So this is always going to be quadratic as a function of r, regardless of whether or not we know that h is a constant, and it's always going to be linear as a function of h. All right, hopefully that didn't get too confusing. I think you'll see in the practice problems your mind won't be blown as badly as that. But there are some practice problems here. Go through, give them a try. If you're getting the answers, which are provided at the bottom, fantastic. And if you're not, make sure you let me know so I can help you out. All right. We will see you in the next lesson. Have a great day.